So I have a child sliding down a 3-meter long slide. Slides inclined at 30 degrees above the horizontal. So the coefficient of friction between his pants and the slide is 0.21. Now that's the coefficient of kinetic friction. How fast will he be moving at the bottom? Now, let's also assume he started at rest, so he didn't get a running jump on the slide. Let's use energy to solve it. So there's my kid at the top. He's at rest. Kid at the bottom, he will have some speed. And that's what we're looking for. Let's use energy. The external work done, or the net work done, the work done by friction or drag or any other push or pull, anything other than gravity or a spring is what that work external is. Gravity and springs are swallowed up in the potential energy term, so we don't have to do them separately. Those are already in the potential energy term. So anything outside of gravity or the spring is our work external. By the way, for those of you who like to have the initials on one side and the finals on the other, do you want to write this equation that way? Because remember, delta U is U final minus U initial. Delta K is K final minus K initial. We bring all the initials to one side. That's what the equation will look like. The work external is added on the initial side because that's what it's affecting. We're either going to add to the original energy the system had, or we're going to subtract from the energy the original system had. Remember, work can be plus or minus, just depending upon whether we're putting energy in or taking it out. If we have positive work being done, we're adding to what was originally there. If we have negative work being done, we're subtracting from what was originally there to end up with whatever's left. So we're going to approach this the same way we have the other problems. We just have one more term that we need to figure out. So we still want to choose y equals 0 somewhere. I'm going to put y equals 0 at the bottom. So yeah, the potential energy at the bottom will be 0. So this is final, so U final will be 0 because of that. Initially, there will be potential energy, mgy initial. Y initial is however high, just vertically, however high the kid started. Well, we know the slide is 3 meters long. It's inclined at 30 degrees, so this side would be 3 meters times the side of 30 degrees. Initially, we're assuming he started at rest, so he will have no kinetic energy initially. Finally, at the bottom of the slide, we're assuming that he's moving, since we've been asked for how fast is he going. So I'm going to make the assumption that he's moving. So that means he will have kinetic energy. So initial kinetic energy is 0, final potential energy is 0. We know the equation at least. We know there's potential energy initially. We know there's kinetic energy finally. We need to figure out the work term to complete the equation. Work. Work is the force parallel to the displacement. So the kid's moving down the incline. What force is making some of the energy not be potential or kinetic anymore? Friction. So we need to find the work done by friction. Friction is up the incline, so it's opposite the displacement, so the work for friction needs to be negative. If the force is opposite the direction the object's moving, then you need a negative sign on your work. The force of friction is the coefficient of friction times the normal force. Normal force, perpendicular to the incline, force of gravity, straight down, friction up the incline. So the normal force in this case will be equal to that component of gravity that's perpendicular to the incline. There's no other forces perpendicular to the incline. So the normal force has to equal mg cosine of 30 degrees. Now that right there is only the force of friction. We're not done. We're trying to find the work. So we have the force of friction. What else do we need to make it work? The distance traveled. I'm just going to call that d. Friction is going to act over the whole 3 meters of the motion. So we need all 3 meters in there. So plugging in, the initial potential energy is mgy initial. The work done by friction is negative mu mg. I'm going to bring the d over. Just put it in front of the cosine. Doesn't really matter. So that's the work done by friction. That has to equal, finally, the kinetic energy that the kid has. So we're still talking energy. The child is starting with potential energy. This negative work means friction is taking away some of that energy. It's not all going to go to kinetic energy. Not all of the potential energy becomes kinetic because friction takes some of it away. Friction takes this much of it away. It takes it away and turns it into, say, heat. The kid's pants will be a little warmer than they were before they went down the slide.
Find out how long he has to slide and catch on fire?
Sure.
Sweet.
Notice there's an m in every term. Mass cancels. Turns out the mass doesn't matter. I'm going to bring the 2 over. Then we need to square root it. And that will be our speed. G is 9.8. Y initial is the 3 sine of 30. Mu, let's see, was 0.21. G is 9.8. D is 3 meters. I get 4.3 meters per second. So the energy, we only have to modify it ever so slightly to account for friction or any other push or pull. We just need to find out how much energy that force puts in or takes out.